Here's about the easiest way to get an air-to-water intercooler. Plus, we're gonna have information about how to set up your water system, and that might be the most important thing of all. We're delivering it on this episode of Engine Masters. Air-to-water intercoolers. These things are my personal favorite implement of induction chilling for boost. Why? Because when you chill the induction air, you make more power, you increase your detonation resistance, and therefore, in many applications, it makes it so you can run on pump gas. How do they even work? Well, this is an air-to-water intercooler right here. It's basically a radiator that you put in the path of intake airflow. So in here, out there. Then, just like a radiator, you pass water through it, and then it chills the incoming air. The thing is, air-to-water intercoolers can come in a variety of sizes. There are enormous ones that are like a piece of luggage you carry in your car. Then there's little itty-bitty dinky ones that we've tried and they don't really work. This is sort of an intermediate-sized one. This one's made by TIC Performance. They actually rate this at 1,400 horsepower. You can get similar things from like 417 Motorsports and other companies like that. What's great about them is that they sandwich between the lid and a base of a Holley high ram intake manifold. They would also work on the low ram or mid ram, but not the ultra low ram. And what this means is, unfortunately, this only works for engines where you can get this intake, which means cathedral or rectangle port LS engines and small block Fords. But if you can make it work, and if it makes power, and if it's great, it saves you so much plumbing. And that's what I love about it. But you can actually make this less effective if you plumb your water incorrectly. That's why we also want to test this 1-gallon water tank against the 5-gallon water tank. Both of them are going to use this little water pump right here. What we're going to find out is if the smaller volume of water heat soaks and degrades in performance as you go. And of course, we know that the big one is probably gonna be better because you can cram a bunch of ice in it. So here's how our testing regimen is gonna go. First, we're gonna run this engine with no intercooler installed. Next, we're gonna sandwich it in there and run it with no water just so we can see if it reduces boost or hurts power in any way. Then we're gonna cycle water through it from the 1-gallon tank, and we're gonna make a bunch of pulls to see if we can heat up the water and see what that does. Then we'll do the same thing with the 5-gallon, and of course the last thing we'll do is cram the 5-gallon one full of ice to see if that's really worth it when you go drag racing. We're doing all of this with sort of what would be a garden variety LS at this point. Everyone has one, right? Turbo up front, 408 in the short block, 9.3-to-1 compression, blueprint engine cylinder heads. It's got a comp hydraulic roller cam that's pretty dinky. It's 225 at 50 on the intake. And of course, we are using that Holley high ram, and the EFI is also controlled with Holley. All right, this is something that we haven't done a whole lot with here at Westech, so we're gonna find out from the Steves if they're digging it, and then we're gonna fire it up and see if we can actually make power with this little intercooler. All right, guys, let me put you in your comfort zone. This is like a super chiller under a roots blower. Right?
It is, exactly.
It's
Like
exactly the same thing. Yeah.
I'm just gonna say boat stuff.
Yeah, we know that works, so we're gonna find out if this works. I think the first thing that we should do is baseline it, then install the intercooler to see if it affects booster performance at all, and then we'll talk about both those things at the same time. Yeah?
I agree.
Okay.
Good starting point.
Okay, make noise.
Time to go.
Yeah. Our first pull without the intercooler installed, we saw 721.2 pound-feet of torque at 5,200 RPM, and then we saw 788.6 horsepower up at 6,500 RPM. Our peak boost was 8.5 PSI, and we saw the temperature in the plenum rise all the way to 147 degrees. Now we install the intercooler with no water in it. Now we can compare no intercooler versus intercooler installed, but no water. We spent a bunch of time off camera chasing this because the results are very interesting.
Boing.
Boom.
Surprise, surprise.
This seems to make no sense. The red line here is with the intercooler installed, but once again, no water running through it. It made more torque, more horsepower. That looks like 737 pound-feet, 808.8 horsepower. The boost actually came down a tenth to 8.4. But interestingly, it actually cooled the air. Remember, it was 147 with no intercooler installed. It's now 138.
More than one time, it cooled the air.
We ran
chased it a little bit.
Here's the story about the temperature in the intake manifold. Black here is with no cooler at all. Look at the red line. That's with the intercooler installed. No water. They start at essentially the same temperature, but look how they diverge. The intercooler is actually cooling with no water in it.
Yeah, and we did that more than once. We started with it higher, and it got closer to the same at the top. It cooled every time. It cooled the air more than without. So I don't know if it's mass, if it's how it's radiating the heat, but it's cooling the air with nothing in it.
I think you're onto something with the mass, because you've got all that aluminum in there that's starting at X temperature. It's going to stay cooler for that short period of time with the air passing through it.
Interesting.
Than nothing being there.
Could be. But the other theory that we had while we were fighting this, because trust me, we looked at air-fuel ratio, the timing didn't change,
No.
the temperatures are the same, the water temperature is the same, so the one conclusion was?
Fuel or air distribution, not fuel distribution, it's a given. But the air distribution, I think the fins in the intercooler help even out and balance cylinder-to-cylinder stuff. I mean, it's the same thing we see in the air hat over a carburetor. It straightens the air, and I think that that intercooler core is doing the same thing over those runners. So I think cylinder-cylinder is better.
There definitely may be something there, but the temperature absolutely did change. You can see it right there in the graph. So that's...
But the curve is also smoother with the intercooler, which is why we started to get the thought about that. Anyway, it's crazy. We installed the intercooler with no coolant through it, and boom, it makes more power. It crests 800. What's gonna happen though when we actually put water through it? The first thing that we're gonna do with water is run the little tiny 1 gallon tank with no ice in it and see how long it takes for that water to not boil, maybe steam, maybe get tepid.
Yeah. Not much there to work with.
Yep, incoming with the water. Here's our first step with water. You can see that I've got a little pump here. It's kind of designed for an OE application. A lot of people use bilge pumps for this type of thing. I like this one better. I found it at Summit Racing. It's actually pretty cool. Now look, I've got a 1 gallon water tank. And the thing is, we're gonna find out that I think the water in here is gonna heat up too much to be effective pull after pull. The reason I did this is I see a lot of people who run something about this size under the hood of their car, and I think we're gonna find out that it's no good. But that's why we test. I could be wrong. All this hose that we're using is dash 16. Brule says he's used like dash 10 or 12 on boat applications where there's a lot of pressure going through it, but Tick Performance actually recommended the 16 for maximum flow. We're gonna fill this with water and no ice. We're also gonna drop a temperature sensor in this thing, so we have data. Here's what's going on now. We've got the 1 gallon tank on there. There's no ice in it. We want to see if it will heat soak. So we're cruising the thing right now at 3,000 RPM and a load of 173 pound-feet. When we do that, we're gonna see that the temperature is gonna stabilize. After it stabilizes, Steve's gonna pull it 5 times in a row. And we're gonna see if that temperature rises and if it keeps getting hotter and hotter. Let's look at the data from the beginning pull that we made after saturating some heat into it and the last pull after we ran it 5 times in a row. The very first pull, the intercooler water tank was 129 degrees and the manifold air temperature was 139. You'll see the same trend of the manifold being hotter as we go to the last pull that we made where the water tank was 158 degrees and the manifold temp was 163. So you can see after 5 pulls, everything's getting hotter. Here's the result on power. Basically, from coldest to hottest, we lost 19.4 horsepower and 27.2 pound-feet of torque. Here are the raw numbers. From our very first pull, 826.3 horsepower and 748.1 pound-feet of torque. And on our hottest pull, 806.9 horsepower and 720.9 pound-feet of torque. Again, basically losing 19 horsepower and 27 foot-pounds.
Hotter is bad.
That's all there is to this. That's all there is to it. Hotter is worse.
Yeah.
I think the next lesson we need to learn, though, is we saw this tank go from 129 degrees to 158. Nowhere near as bad as I thought it would be, by the way. The question is, will the 5-gallon tank not saturate and not heat up as quickly?
Well, that seems like a common sense conclusion. I say that's what's going to happen.
Yeah, but
we have to see.
That's kind of the way this whole thing has been.
It is, yeah. Okay, heat is bad. We're gonna go find out if 5 gallons of water makes heat less bad.
More water.
Or less heat.
Okay, here we go. 5-gallon tank. It's gonna be a lot more water capacity and it'll probably stay cool longer than the little 1-gallon jobs.
This one's an actual intercooler tank, which you can tell because of the size of the opening, so you can get ice in it easily. Yeah. The bottom line of everything that we just did is that the larger tank is better no matter what, because it has cooler temperatures no matter what, right?
Yeah,
Right.
the larger tank is just better all the way around as far as how long it takes, how cool everything is. It just maintains it longer. It's just better.
It's a bigger heat sink, basically, is what you're dealing with. 5 gallons versus 1.
So let me give you the actual data. Let's look at degrees first. This is going to be the first pull and the last pull of the sequence with the large tank. The intake manifold plenum temperature on the first pull, 114 degrees. On the last pull, 132. That's a gain of 18 degrees. It's roughly the same as what we did with the small tank as far as the total gain, but it's cooler overall. If we look at the water in the tank, on our first pull, it was 93 degrees. On our last pull, it was 119, a gain of 26. Again, very similar in the overall gain from the small tank, but radically cooler overall. Now let's look how that affected the horsepower. On our very first pull, we saw 845.2 horsepower and 769.1 pound-feet of torque. On our last pull, 823.2 horsepower, 748.6 pound-feet of torque. We lost 22 horsepower, and 20.5 pound-feet of torque. And that's what you're seeing right here on the screen. The red is the hottest run, and the black is the coldest run.
Yep.
Yeah. And also, guys, here's what happened when we looked at 5 poles. The big tank was worth 16 horsepower and 27 pound-feet over the small tank.
That's amazing.
And it was worth more than that when we were running it cold. And if you put that big tank in your trunk, you're gonna get it away from the engine compartment, because my belief is you got a 1-gallon tank in the engine compartment, that thing's gonna be 180 degrees before you even go.
It starts there.
Yeah.
Right.
And only goes downhill from there.
It does.
Yeah.
Keep it cool and everything's going to be a better day for you.
Ultimate answer is the larger the tank you can get. As you said, it's the biggest heat sink. It's going to be way better off for you. Last thing we have to do, just because, is make more than 850 horsepower by stuffing a bunch of ice in the tank, and then we'll be done for the day.
It's what every drag racer does.
Should
do
do
it.
every time. Excellent.
The Mad Fry Burger.
Oh, man, that was good. Good to the tune of 814.1 pound-feet of torque and 864.9 horsepower. And then the temperatures with the ice in the thing. The water in the tank started at 32 degrees and only went to 34. In the plenum, 68 degrees to 80, way cooler. So all of this coolness, all of this horsepower, the thing we haven't touched on is the tune-up. You had to tweak it every time we got things cooler.
Yeah, as the air gets denser, there's more oxygen, so you got to add more gas to it. And the last whack I rolled in once, and it was a full ratio leaner. So I had to throw quite a bit in, about 80 horsepower worth.
That's really interesting, actually. If you've got a tune-up on a chassis dyno with a bunch of ice in it, and then you run around with no ice in it, it's going to be pig fat. Yeah.
Particularly if it's not in closed loop, you know, and you're running a regular tune-up.
Which is way better than tuning it up with no ice and then pouring ice in it and having it be way lean. That was awesome.
I'll bet this is going to be the easiest episode you have ever concluded concisely.
It's the most complex episode I've ever tried to explain with all those numbers, but it's the easiest to conclude. Before we do, call up A-Test, because basically, if you're driving around with no intercooler, what you want to do is add an air-to-water intercooler and add a water tank and add ice to it, because look,
Wow.
look at that. All other things being equal, that is massive power.
That's the first time I've seen that. That's just obscene.
It is
that's huge.
absolutely absurd. Just to give you a point of reference, with no intercooler, we made 788 horsepower. With that intercooler and water and ice, 864. What are you doing with your life if you don't have one of these
Is that
things?
80 horsepower? Is that what you just told me?
No. Oh, is it?
784 to 864?
Close. Man.
That's a lot of horsepower.
Ridiculous. And it makes it so that you can drive it on pump gas easily.
Jeez.
Easily. 8 pounds of boost. Man, that's pretty awesome.
And yeah, with no change in boost, no change of anything other than just air inlet temperature.
That's it.
Pretty awesome.
You know what? You just pulled it down to the actual kernel of truth, which is all you really needed to know, which is get your intake temperatures as cold as you possibly can.
Yeah.
Whew, because that's when you make the big power like we like to do every time on Engine Masters. Okay, make noise.
Time to go.
Yeah. Tight.
Boom. That's right.
That was huge on the torque. Did you see that?
I was looking at horsepower rolling in, and I saw pretty big.
That's massive. 90mm throttle body versus 105 versus a tunnel ram with a couple of throttle bodies and a 442 cubic inch LS7. All of that this time on Engine Masters. How much throttle body airflow do you need for your EFI engine? Well, that's what we're here to find out this time as we test a 90mm versus a 105 versus 2,000 CFM worth of top-mounted dual quads with EFI. Actually, in this episode, you're gonna learn 3 things. First, you're gonna find out the power difference between the 90mm and the 105mm. Then you're gonna find out the difference between the forward-facing throttle body with a 105 versus the tunnel ram with dual quads. And the third thing is a combination for a killer 442 cubic inch LS7. Here's how we're gonna do all that, using the same Holley High Ram base. You see, that intake manifold will handle either this lid for a forward-facing throttle body or that one there for the dual quads. So nothing else is changing except for the top of the intake manifold. Also, Holley does offer this lid right here designed for either a 92mm throttle body or a 105. Now, in this case, we're using the 105 for both tests because the smaller throttle body will work on the one with the larger opening here. So that's another sort of step that we're taking to make a clean A/B test between the two throttle bodies. This is really just like a carburetor CFM test. And if you're familiar with carburetors, you know that typically the larger the throttle blades, the more CFM of air they're capable of flowing. The same is true of a throttle body. It's just that they're ranked a little bit differently. They call it like a 90mm, and that is the metric diameter of this throttle valve that is inside the throttle body, or the butterfly. Usually, bigger is better, and bigger flows more air. What's interesting is that these two are ranked by a millimeter diameter, whereas these 4-barrel throttle bodies are ranked by CFM. They're 1,000 each. Steve Dulcich did me a favor and calculated the area of each of these in square inches so you can kind of get an idea of what's really sort of the range of difference between 90mm and 105. Check this out. The 90mm throttle body, right there, the square inches of that is 9.85 inches. It jumps a lot more than I expected when you go to the 105. That is 13.4 inches. Pretty wild that you go from 9.8 to 13.4 with that change. Now, when you do two 1,000 CFM 4-barrel throttle bodies, you get 19 square inches. Now, just to sort of put that in carburetor terms, for those of you who might be more familiar, a 1250 CFM Dominator, that would be 14 square inches of butterfly area. It's not really a comparative analysis because the Dominator's got boosters in the way, so the airflow is not exactly the same, but it sort of gives you the idea. To test all of these, I knew that I was going to need an engine that made a lot of airflow. Really, if I'm not taxing the limits of the 90mm, then I'm not proving anything. Because if the engine only needs 90mm, then adding more and more and more, area to the throttle valve potentially isn't going to make a difference. That's why I wanted something that was going to make north of 700 horsepower. That's what we got when we borrowed this engine from American Heritage Performance. The bottom end is a stock LS2, like, typical GM LS engine. It's a factory block, but it has dart and sleeves that allow for a bigger bore. The bore and stroke is 4,130 with a stroke of 4 1/8, 4.125 inches. That adds up to 442 cubic inches. The cylinder heads on this thing are LS7 style, but they're a custom CNC ported unit by American Heritage Performance. The camshaft in this thing is also an American Heritage custom made by Comp Cams. It's a hydraulic roller camshaft. The duration at 50 thousandths tap at lift is 245 on the intake and a big 266 on the exhaust. There's a large spread there because the intake port is so much better than the exhaust side. The lift is 660 on both lobes and it's on a 115-degree lobe separation angle. The one thing I've held back on you is this engine is 14-to-1 compression. It's got scat cranking rods, Racetech pistons, and typically American Heritage builds these things at lower compression like 12.5-to-1 and runs them on 91 octane. And so Steve Brule has some anecdotal information on the power difference between the two different compression ratios, and that's another bonus bit of like tech info that you're gonna get at the episode as soon as I sit down with the Steves. And once we chat a little bit, we're gonna be making noise with 442 cubic inches of LS7 power. It's a big moment. It's the very first LS7 we've ever had on Engine Masters.
You were wanting a big motor to test big air.
I think we had to make horsepower to make this a realistic test.
We have a customer who tests a whole bunch of these LS7s, and they're generally pump gas versions. And they make big power. They're 440 inches. They make 700 horsepower on 91 octane.
You told me with 12-to-1 compression on 91.
Yes, on a factory computer. He puts them in Corvettes and stuff and very successful with them. It's American Heritage. Coley was kind enough to lend us his personal engine that he's building for his father.
Yeah.
So we had a little extra time with it. So we've got a 440-inch LS7.
Yeah.
That's big and makes good power.
And it's sort of anecdotal, but we have another test that we can talk to you about. This thing's 14-to-1 compression.
Right.
He normally runs 12.5 on pump gas.
12.
With the same combo, so you kind of know the difference. What happened?
Well, it seems as though the returns were diminishing after 12-to-1. We picked up like 30 horsepower with 2 more points of compression.
Yeah.
And we've talked numerous times about that sweet spot, that 4% stuff being between 8 and 12. And I think this kind of bears that out. It's not as big a percentage on the bottom side of that, and certainly not on the top.
You mean the percentage of horsepower improvement
Yes.
going from 12 to 14?
Exactly.
If you look at the
Yeah.
curve, it is like that.
Yeah.
You go up in compression, it
Ever
flattens
diminishing.
out. Yeah.
Yeah, I wouldn't bother. For
Same
30
thing with-
horsepower on
No.
a streetcar, I would just run it lower compression.
Well, after
Right.
our conversation, Coley decided he's not going to either in the
Perfect.
future.
Okay.
Okay, so there's a little bit there. But what we're doing here is airflow testing, and right now we've got the smallest throttle body on it, so we're gonna fire it up and get ourselves a baseline.
Perfect.
We're about to run this with the 90-millimeter throttle body, and then we will switch it over to 105-millimeter. Then we'll come back and show you the results of both.
Time has come to say goodbye to the 90-millimeter throttle body and replace it with the 105. I think it's going to make a difference. We'll see if I'm right or wrong. With 15 millimeters more throttle bore, that should let more air into the engine and make more power. Steve's gonna fire it up, and we're gonna find out right now.
It really made a difference.
It liked it.
Yeah, it did. Let's start by looking at the pull with the 90-millimeter throttle body. Pretty stout engine with a good spread between the RPM at peak torque and the RPM at peak horsepower. At 5,100 RPM, this thing made 595.3 pound-feet of torque. All the way up at 7,100 RPM, it made 732.2 horsepower. That's all with the 90-millimeter, which means nothing to us until we look at the overlay with the 105.
Pretty good, but maybe
It's
not.
good,
All the way.
But
Now it's much better.
that's better.
That is way better. Our power numbers with the larger throttle body are a little bit deceiving because the torque curve is so flat down at the bottom that it ends up giving us a peak all the way up at 6,200 RPM of 598 pound-feet. But honestly, you could call this the torque peak down here at 5,100 also. And then up at the top, we're still looking at 7,100 RPM, but now we're seeing 741.5 horsepower. Clearly, the larger throttle body was the way to go.
You know, your idea of needing a bigger engine is, I think, absolutely on target because we wouldn't have seen this on a 370-inch engine that makes 500 horsepower. And I'm really comfortable that it is an airflow limitation with the 90 millimeter because it's a dead overlay down here where it doesn't need the airflow and the curve diverges. The other thing that tells me that is we had to touch the fuel a little bit to make up for the added air.
What Steve's talking about is that the airflow demand is so much less at lower RPM and lower power that the difference in the throttle bodies doesn't make a difference, but then it starts to come apart. In looking at that, is there any kind of a clue that we can take about what horsepower you would run with the 90 millimeter throttle body?
I don't know, I guess where it diverges might be a pretty good indicator of how much power that is.
Which is about 575-ish, 600-ish?
Yeah, so at 617, that's where it's really saying, I'm making a difference now.
Yeah.
So again, the 500 horsepower motor that we didn't borrow wouldn't have shown us these results and wouldn't have shown us the truth.
Exactly.
No, you need to tax the airflow demand or the airflow delivery of the throttle body to really see a difference. And this engine can do it. Your little street driver won't, right?
So I think our final conclusion here is that 90 millimeter works up to about 600 horsepower. And remember, when we're looking at that, RPM doesn't matter, displacement doesn't matter. Horsepower is going to consume not a fixed amount of air, but a roughly similar amount of air, regardless of displacement and RPM.
Whether, let's say, it's a small engine that goes 8,000 RPM or a big engine that goes 5,500, if it's moving the same amount of air because of cubic inches and engine speed, again, it's that 600 horsepower.
That's going to be your best metric.
What makes me happy about this is we're not the first guys to ask this question.
Right.
I think we're maybe some of the first that answered it because, you know, it's been tossed around a bunch. Does it matter? Does it not matter? I don't think you're going to see something. Oh, I think you will.
Yeah.
And now we know the answer.
Here's the other consideration, though. People might ask, what would be the downside of just putting a 105 on my 500 horsepower engine? And I think that comes down to drivability and tip-in. There's so much throttle valve area on the 105 that actually Holley has got that special curve in the shape of the opening of the throttle body billet in order to prevent that tip-in from being really aggressive.
That real snappy feeling. And, you know, guys, early on in the Mustang era even, you know, guys would put a bigger throttle body on, and they thought they'd picked up power. All they were doing was picking up throttle response, and then it did nothing after 3/4 throttle. It just didn't matter. But it made it happen a little quicker because of, like you say, the area of the throttle body.
We're talking all about airflow while you can probably hear the airflow happening outside. The doors rattling like crazy in here.
It happens every once in a while here in Maryland.
Next thing that we're gonna do is change the lid on this thing and put on the dual throttle bodies, and man, I hope it makes a difference. I want it to win.
Well, if it's a tunnel ram, you'll want it to win.
Exactly. Although, you know, there's arguments both sides. This is lower profile. The other one is gonna look way cooler.
You know, I don't know. This is a pretty good look right here.
It looks pretty good to me like this.
Yeah, it's not bad.
Yeah.
Right, here comes our changeover to dual throttle bodies. The cool thing about these Holley high ram intakes is that the top of it is interchangeable, so all we're gonna do is unbolt it right here, separate the lid, and install our new dual quad throttle bodies. Immediately better. All right, the dual quads are installed. We got 2,000 CFM happening right now. We also have the air flowing directly down into the cylinders. I think it's gonna make more power, but what does my opinion matter? The dyno's gonna tell us. complete.
Yes.
Dual quads on tunnel rams work even
Every
with
time.
EFI. Every time. It doesn't fail. How great was that? Let's find out how great it was, because I know it was great.
I know it
pretty
was.
Yeah.
I know it was too. Just once, I want you to be wrong.
Okay, Steve, here's how it works. I find the thing that always wins, and then I just attach myself to it. That's why I do shows with Dulcich.
That's right, Bert.
The power numbers with the tunnel ram are finally 600 plus pound-feet of torque. We got 604.7, and once again, it's up around 6,100 RPM, but you can see the curve is very flat, and so you've got that power everywhere. And up top, still at 7,100 RPM, we made not 750, but 748.7 horsepower. Compare it to the 105, and you can see that the tunnel ram dual quads was way better.
Same trend. Doesn't need the air down low, needs it more up high.
But it's separating sooner,
Yeah.
because it's making a little more power, maybe?
Well, that could be quality beer. I mean, I know that higher engine speeds are higher air speeds. And so alignment and those things, turns and radiuses and all of those things start to become more critical with higher feet per second air speed than at low engine speed. So
We were talking about how with the, anteater, the air doesn't want to make that hard south turn right into the front cylinders. It's probably cramming all the way to the back.
Well, a lot of guys will think that the air is somehow rushing in and hitting the back of the manifold. It doesn't really work that way. It's not like it's running through the air at 100 miles an hour. The engine's drawing the air in.
Right.
But there's still more abrupt turns to make than a nice, perfect, straight alignment. So the quality of air, look, we see it on the flow bench. When you have a nice, smooth radius and it's long and straight, it flows more air. So it's going to do the same thing.
What he's talking about is if you look at the layout of the throttle body to the cylinder, it is a straight line from the throttle blade all the way to the valve, instead of having to make a turn, which is what you would do with the throttle body.
Which probably
setup with a
helps
forward throttle body.
distribution, too.
It's got to. We don't know that.
I can be
quads.
fairly certain that it doesn't make it worse. So-
Yeah.
Yeah. Let's have a look at the 90 millimeter just so that we can. Okay, there you go. The blue lines here are the 90 millimeter front mounted throttle body. How could you even live with yourself putting something like that on this engine? Although in truth, I don't think the average guy who's building a 700 horsepower plus LS is going, oh, I'll get the smallest throttle body on the market. They're getting the 105.
Right, absolutely. And while this graph kind of illustrates exactly what's going on and it's fairly defined, it's not a huge difference in peak power. We're looking at 41 to 48, 7 horsepower at peak, and sometimes the packaging just doesn't allow this.
It's true. This isn't a look that a lot of guys want for their car, and they don't want the hole in the hood and everything else. But, I mean, they're wrong, but they can have that opinion.
Mr. Snuffleupagus is fairly attractive as well.
It is pretty good, I have to admit. In addition to what we saw in power here, you told me you were looking at the manifold vacuum, and it showed the same trend?
So when Ishmael actually started looking at the data, it kind of qualified what we had to do as far as making changes by adding some fuel because the engine was moving more air.
To richen it up for the tune-up, okay.
Yeah. And so when we went back and looked, he had data logged the run, and it had 4 kPa, which converted to inches of mercury vacuum. It was basically an inch of vacuum. Restriction still.
With the 90 millimeter?
With the 105 millimeter.
Even with the 105?
Yes, it was even greater with the 90. So moving up, and that's, again, it showed us the power increase, not so much at the bottom where it doesn't need the airflow, but up at the top where it was a restriction. Now there's not, and so it picked up some more power.
Interesting. What we're talking about there is if you look at manifold vacuum, usually if there is a restriction above the intake manifold, you'll see that at wide open throttle at high RPM, it will actually be pulling about an inch of mercury, or, if it's a bigger restriction, it'll pull even more.
Yes.
But you're saying with 2000 CFM up top, it didn't have any manifold vacuum.
No, 2000 CFM was enough.
Right. It tends to tell us that that's enough throttle valve area.
Well, you go back and you look at some of the things that just didn't make sense at the time, like Bill Jenkins running 2 Dominators on a 331-inch small block, saying it just doesn't need that much air. But when there's no restriction, the engine makes more power.
Yeah. So the reasons that we think that the dual quad setup made more power are better alignment of the airflow down the barrel and into the cylinder, and therefore also giving us sort of a more even air-to-fuel distribution cylinder, which is a guess, but we think that's true. And we now have enough throttle valve area that we're not imposing a restriction to airflow for this particular engine.
Agreed on every point.
Yeah,
Yep.
I think that pretty well sums it up.
Now, let's talk about boost. I've never seen a turbo guy or a ProCharger guy or Vortec guy run a hat on 2 throttle bodies on top of a tunnel ram like this, and why not?
You know, it's kind of interesting, but once the manifold is completely under pressure, I wonder if it does the same thing once there's pressure in the hat versus actually the engine drawing air through the
Still flow.
I think it's the same thing.
I think it's the same thing too. I mean, the air's still moving, it's still flow.
Yeah.
Just because it's pressurized doesn't mean it's stopped moving.
No, I agree.
It's still got to move, and it's got to move more air through it.
Yeah.
Most of the turbo and boost guys are using that Holley, forward throttle body lid.
Yeah, agreed.
Well, it's easier to plumb, for one thing.
So I think here's what we've learned overall. First of all, the 90mm throttle body, by our dead reckoning, is good for about 575 to 600 horsepower-ish. Second of all, if you've got 700 horsepower, you really want that 105, or honestly, even a little bit more, because we were still pulling vacuum with the 105.
Yes.
So I don't know, maybe start porting some stuff here and there. Or
Maybe someone's going to make a 110.
Maybe they will. You need a little bit more. And then, of course, with the tunnel ram and dual quads on top, we've talked through why the multiple reasons are that it made the best power overall.
Good stuff, really. And once again, you win with the tunnel ram.
Hey, it's inevitable, Steve.
I know.
It's a foregone conclusion.
Horsepower, it's kind of inevitable because it's what we seek every single time on Engine Masters. Uh-oh. I've got one in, Steve. 3 points define a plane.
Yeah, but you don't need to define a plane here. All you need is 2 bolts to line it up.
Yeah. 2 bolts define alignment. Well, I get, 1,740.
Well, we're within 5,000, Steve.
Yeah.
Confucius say man with too many watches never knows what time it is.
Do these weird widgets make horsepower? We are gonna find out, blown and unblown, on a pretty wicked small block Ford, this time on Engine Masters. Here's what we know. Increasing airflow through an internal combustion engine improves power, even when you increase that airflow in minute ways. You know this from the legendary Engine Masters Salad Bowl. We've put this on top of carburetors in a number of tests, and it has never failed to make power. Sometimes it's just 2, sometimes it's 5 to 7, but the whole point is that we're making that carburetor more efficient by giving it a dish to direct the airflow. That's basically what this episode is about, but with EFI, we're gonna find out if these doohickeys right here can make added power. These things would be called a number of things. They could be a bell mouth, they could be a volute, they could be a radiused entry. Some might call them a velocity stack, although that's a little bit old school. The thing about them is you can either put them on the front of an EFI throttle body, or you can stab them on the inlet side of a turbo or a centrifugal supercharger. So those are the things that we're going to test, both NA and blown, with and without the volutes. Other things that you're gonna get in this episode are gonna be 2 different power combos for a small block Ford, plus you're gonna see the comparison of blown versus unblown. It's gonna be pretty meaty. All right, let's talk about the engine that we're gonna be testing today. This is a 363 cubic inch small block Ford from Dart. It's based on the architecture of a 302 or 5-liter pushrod Ford. It's an aftermarket block from Dart from their SHP line, and that's what allows it to have a bigger bore than you would normally get from any production 302. It's a 4 1/8 bore, and the stroke is 3.4 inches for 363 1/2 cubic inches. The compression ratio on this is 10 to 1. The cylinder heads are also from Dart. They're their Ford head with a 225cc CNC ported inlet runner. The camshaft in this thing is a custom comp cam solid roller. The duration at 50 thousandths tappet lift is 244 on the intake, 258 on the exhaust. That's a really big split. It's on a lobe separation angle of 113 degrees, which means that this thing will RPM. It'll go to 7,100 RPM naturally aspirated, and the lift is 600 both on the intake and the exhaust. Now, we've run this thing with a carburetor almost always, but now we've got the Holley high ram on this thing for the very first time. Here's the thing about the intercooler. We are going to run it in the naturally aspirated setup. Now, we don't really know if that's going to help or hurt power. Maybe the fins in the intercooler are an air restriction, or who knows? Maybe they're actually straightening out the air and making more power. We don't know. But we're gonna run it that way anyway because it's still gonna be a solid A/B test. Now, another thing that could be limiting the naturally aspirated horsepower on this thing is that we're running a fairly small throttle body. That is a Holley 90mm unit. Probably a 105 would be better, but the fact of the matter is, we had a bell mouth that was going to fit on this perfectly. So that's what we're running. All right, that's the deal. Later on in the episode, I'm going to tell you all about the supercharger, but right now, I'm going to have a pretty interesting discussion about dyno stuff with the Steves, and after that, we will fire up the 363 in naturally aspirated trim and find out if the official doohickey of airflow is really worth power. It's freezing in here.
You came from Minnesota, you came from Florida. I came from Harupa Valley, which is more exciting.
It's cold, which brings up something that we normally don't talk about on the show, which is correction factor.
There's SAE and STP.
So what is the STP, standard temperature and pressure?
2992 barrel, 60 degrees, 0 humidity.
So the dyno test results are corrected for atmosphere, basically, for a barometric pressure of 29.92, and what did you say the temperature was, 60?
60 degrees.
Right, and so what happens is when the weather is really good for making horsepower today, you don't get much of a correction factor. If it's really hot, and if there's, not a lot of air pressure, then you get more of a correction factor. Why do they do that? It's so that you can compare engine horsepower, say, in Denver versus Death Valley, and the two different conditions can be compared equally as far as horsepower goes.
Yeah.
Is that right? And FYI, another thing that we try and do on the show is make sure that we're doing our tests on the same day, in the same weather conditions, so even with the correction factor, it's apples and apples.
Just trying to reduce variables. When we're sometimes looking at twosies, threesies, it becomes important to make sure it's a level playing field.
Ready to fire it up? See our baseline with no doohickey?
With no salad bowl facing forward?
Right.
Yeah.
Yeah.
Sure, let's go.
Okay, here we go with the volute, the bell mouth, the doohickey, the reverse salad bowl. All right, will it make 500 horsepower now? No. Let's see the baseline. Going right to it.
It's still fun because sometimes the things that don't even surprise me are still fun.
Here's our baseline horsepower from the 363. We made 416.6 pound-feet of torque at 5,200 RPM and 490.6 horsepower at 6,700 RPM.
Not much to say.
No, that's it. Dulcich was looking how it flattens out at the top of the curve. Do you have a valve spring concern there?
Nope.
Nope.
That's not a valve spring thing. That's just a motor thing and airflow.
It's just a motor thing. Now, we're gonna have a look at the bell mouth power. And it's a little bit better. The red lines here are gonna be with the bell mouth on the throttle body, and now we've got 420.2 pound-feet of torque. Interestingly, it dropped down to 4,900 RPM. Up top, we've still got a 6,700 RPM peak, but now it's making 497.2. You can see that the power gain with the bell mouth starts to separate right here at 4,800 RPM, and it grows bigger and bigger as the airflow demand increases with more RPM.
Like I say, sometimes just the most simple things count. And you start adding up a lot of little details, and all of a sudden you've made a whole bunch more power.
Yeah, it made a difference. I mean, 7 horsepower.
And that was the easiest changeover we've ever done.
Completely.
Yeah, that was a whole hose clamp, Steve. What are you talking about?
Let's talk about why. This thing has a 90mm throttle body on it. I think that might be a restriction for 500 horsepower, somewhere in that neighborhood. So perhaps the bell mouth helps it enough to give it a bigger gain than we might see on another engine.
There's also turbulent problems too when you've got a sharp edge and air trying to move past it. Steve and I were discussing that earlier, and for the same reasons you port a cylinder head and make entries and radius and things smoother, the air travels better.
Well, it's the sharp-edged entry. You have the venturi constricti effect. And basically, that means that the air is coming in and it's coming from all around, but it has to navigate that sharp edge, so the effective diameter is reduced of the throttle body. Whereas with the radius, it has a surface to follow going in, so you're taking advantage of the full diameter.
Makes perfect sense to me. I mean, it's got a 90mm throttle body on it with the volute, and maybe it's a 78 or 80 without, actually, by the time the air has packed around it and reduced the size of the entry.
And more turbulent because it's going over that edge and stuff's going around like this. So yeah, the bell mouth is just good. And honestly, this is the fuel injection version of the salad bowl that we've seen on the carburetor so many times, but it picked up more power. 7 is pretty good. Salad bowl, I think we've seen 2 to 5. Yeah. Now I'm gonna go tell you about the supercharger we're gonna use, and I suspect that the bell mouth is gonna make a way bigger difference with boost. And now we move on to one of the greatest loves of my engine master's life, and that is the centrifugal supercharger. This is essentially like a belt-driven turbocharger. You can see that it's got an impeller right here. Air gets sucked in there and crammed out here and into the engine. This particular one is a ProCharger model F1A94. If you look at their catalogs, they consider this the top of the line for their street superchargers. This thing has a drive ratio in this case of 1.61 to 1. Now, there's also a gear reduction inside the supercharger of 5.4 to 1. Do all the math and assume that we're gonna run this thing to 6,500 RPM, and the supercharger is running at 56,500 RPM. Now that sounds pretty cool until you realize that the limit of the F1A94 is actually 74,000 RPM. That means we're not really running this supercharger in the sweet spot. And the truth of the matter is that could affect the outcome of our test. It's not really taxed at the absolute limit. Now, speaking of maximums, like that 74,000 RPM, if you look at the ProCharger catalog, they recommend this thing up to 1,300 horsepower. The truth is, every time I've run a ProCharger, they usually make a lot more power than what they rate them at. And you can usually run them at just a speck more RPM than they say, although don't tell anybody I said that because they're not going to agree to it. The other maximum on these is 36 PSI, and we know that we're going to be running this closer to 17 PSI. So once again, not at all at the limit of what this thing can do. One important thing about the ProCharger design is that it has an internal oil supply, and that means that you do not need to run like a pressure line from your engine into the supercharger or a drain back to the oil pan, and I just find that super convenient. That's one of the reasons I love this thing. You just completely bolt them on the engine, done. I definitely want to run one with an intercooler though, and in this case, we're going to be using the TIC Performance sandwich intercooler that goes in that Holley high ram intake manifold. The last thing that you should know is we're going to be running this with an 8-rib drive belt. Now, ProCharger has gone through and upgraded a lot of their drive systems, and they swear to me that you can run an 8-rib belt up to way north north of 1,000 horsepower. Of course, what we're going to be doing is testing the ProCharger bell mouth on the inlet side of this supercharger. It's going to end up going right there. But of course, we're going to run it first without the bell mouth and then with. And I hope we see a big power gain. All right, let's roll into the dyno, and Troy's gonna hang this thing on the front of the driver's side cylinder head. Easy as that. We'll throw a belt on it, and then we will start making boost.
Oh, you got that on there pretty quick.
Three, yeah. One might think that we've done this before, once or twice. Boom, that easy.
We have our ProCharger centrifugal blower installed. Now we're gonna run it for the numbers and see what it does.
How come it makes like twice as much power?
Oh, because it has twice as much pressure.
That's right.
Twice as much air.
Let's look at it. Ooh, nice.
Wow, it is.
This is typical of what we see with the ProCharger that has a just dead rising boost curve. Peak torque and peak horsepower are at the same RPM, which is 6,500, which is where you stopped the pull.
It actually would probably be peak torque at 6,500, and this thing would just keep heading north and for another 500 or so with power, but 363 inches, 1,000 horsepower, that's a pile.
Pretty crazy. Well, that's actually 948 horsepower.
Yeah.
Here are our final power numbers, both at 6,500 RPM. We made 766.6 pound-feet of torque and 948.7 horsepower. So let's have a look at the boost curve. A peak of 17.3 PSI, which makes sense. It's actually not fully efficient. I think we would double the horsepower at 14.7 PSI, 15 PSI.
Theoretically.
Yeah, theoretically. Obviously, there's losses.
You're never gonna get there, but.
There are some parasitic losses even with the best blowers and...
Oh, sure.
Yeah.
Now let's talk about the tune-up, which is really conservative to keep this thing from scattering.
The air-fuel ratio is more in the middle tens, just trying to be conservative, do some thermal management. We could make more power if it were a touch over 11 or even 11 and a half. The timing's only at 26 degrees. I think we could push it to 29, maybe even 30 and make more power. But you know, it takes a lot of time pulling spark plugs and doing all of those things to make sure it's safe and okay at those numbers. Instead of just arbitrarily going there and having a problem, I'm not willing to do that. So we're just being a little conservative because horsepower isn't specifically what we're testing as far as related to the tune-up.
A/B comparison on airflow.
Exactly.
And so basically you're running the thing much richer than you really need to, and you're not running as much timing advance as you could, but you're keeping our engine in one piece.
You always say it so much more clear than I do.
Well, after you train me. Right, now we're gonna go install the bell mouth and see if it makes more power. Go.
As you can see here on the ProCharger, we just have an open air inlet, and I'm gonna add the radius entry. It's just a hose clamp away. One of the things I always like to do is make sure it's good and tight. The only thing left to do is fire it up and see if it helps horsepower.
Here's our power with the bell mouth on there. Again, both the power peaks are at 6,500 RPM. We got 974 horsepower, and the torque, 787. None of that means anything till we compare it with the non-bell mouth pull. Oh, look at that. All right, the red lines here are with no radius entry or volute or bell mouth. I've called it everything throughout the episode. And the black lines are with.
Yeah.
So you can see that it begins to diverge down here right at 5250. And then on the way up, as the RPM increase, the airflow increases, they begin to separate.
And the demand.
What is the difference there? 949 to 974.
Yeah.
That's 25 horsepower.
I got to admit, I'm disappointed. I thought it was a way bigger difference than that based on past experience.
You know, all the times that we've messed around with these centrifugal superchargers, we've learned to control a lot of the boost and power numbers on the inlet side, but we've normally done it by restricting the inlet.
Yeah.
This time we're trying to help the inlet, and so this is not honestly a huge surprise to me. It just shows me that all the little things can add up.
Slowly add up.
And if you're trying to make the most out of it, let's say an undersized blower, because that's what you have, probably help more in that kind of scenario.
Yeah, this thing you can make more power than that with the tiniest change in pulley ratio.
I mean, we've got it turned down.
The thing we do know for a fact, though, from past testing is that an air filter, as you were saying, on the inlet side is a restriction and will really harpoon your horsepower and your boost.
When we were trying to test leaks in one episode, we actually didn't want to make 1,000 horsepower, so we started by restricting the inlet side with just a smaller air filter and dragging it down. And it knocked, what, 150 or 200 horsepower out of the thing. So it's the right way to control power if you want to go down. Obviously, if you want to go up, that's the right size blower and the right pulleys, and you can do about whatever you want.
I think the lesson that we learned is that inlet restriction on one of these blowers is way worse than what you gain from putting the bell mouth on there. But speaking to the guys at ProCharger, they're like, the more power you make, the bigger difference this makes.
Well, and I think that kind of just stands to reason. If there's no demand, then it's not going to make a whole bunch of difference. But at 1,500 horsepower or 18 or 2,000 or whatever, that becomes a real critical area.
Because like you said, it's a diverging curve, so.
Let's have a look at the difference in boost between these two. I'm thinking it's nothing like what I expected it to be. I'm just all about being wrong in this episode. Okay, black line is with the bell mouth, red is without, and you can see we got about half a pound extra boost up at peak.
Yeah.
I thought it would be 1 or 2.
Yeah, like I say, it doesn't surprise me. We have a little difference there just on kind of what our expectations were, but that's what makes it fun.
So, final conclusion, I don't think I want to say that the bell mouth always works, but I think the higher your power level and the worse your sharp edge on your inlet, the more likely it is to work.
I think what I'm taking away from this is really more that small details do count.
Right.
And attention to detail in every aspect of your engine. If you just kind of give it that little bit of love rub, you have a lot more potential for something being right, not breaking, and making more power.
And I want to go back to blower sizing too, because if you have a smaller blower that's giving all it's got, then that could help more.
Become more critical.
Yeah.
The same way I said that the 90mm throttle body maybe showed more of an advantage than if we had a 105 on it.
Probably.
Yeah. Little tricks to make more airflow. More airflow can make more boost, and all in all, it makes more power, which is our goal on every episode of Engine Masters. Okay, here we go with the volute, the bell mouth, the doohickey, the reverse salad bowl, the incompetence. I thought this was going to install. What am I doing?
Just waiting for him?
I've been ready. All right, here we go.
Yeah.
Did you hear action? Use that one time at a time.
The quickest supercharger installation ever.
What are the pros and cons and power of sequential versus batch fire fuel injection? You will know by the time you're done watching this episode of Engine Masters. I wanted to know, so I figured you would too. Is there a horsepower benefit of sequential electronic fuel injection versus batch fire? I mean, sequential just seems so much more sciencey. The thing is, when we actually got into it with some guys who are EFI experts, including people inside Holley EFI and even Fast, all of a sudden there was confusion over what batch fire even meant. Honestly, sequential is easier to understand and explain, so that's what I'm gonna do first. Of course, we're talking about engines with multi-point electronic fuel injection. What does that mean? It means that there is an injector in the intake runner right above the port in the cylinder head, and there's one in every cylinder. Of course, in an 8-cylinder, you typically have 8. You can also do multiples of 8. You can run 2 per runner and everything else. We've got 1 injector per cylinder. With sequential EFI, the computer tells each injector to fire or to send fuel into the engine every 90 degrees of crankshaft rotation, and it does it in the order of the firing order. For example, on the LS engine, 1872653. I know, ignore this right here. It's not what it is. It's a little bit different for the LS engine. So that's what it's doing. It's like precision pinpointing the fuel into each cylinder as it needs it. Or is it? Well, that's what we're gonna find out. But then there's batch fire, and this is the thing where we got different answers from different people. Basically, the way I derived all the info I got is that batch fire means you're firing more than 1 injector at the same time. You could be doing pairs, you could be doing 4 at once, you could be doing all 8 at the same time. Sometimes, batch fire really comes into play with throttle body fuel injection, where the injectors are in the throttle body up on top of the engine, not multi-point. But there is batch fire with multi-point as well. As a matter of fact, what we usually do, what you've seen actually every time we've done EFI on Engine Masters, is what's called bank to bank, and that's what we're gonna do here. Bank to bank means a whole batch of 4 injectors on one side of the engine fires, and then the other batch fires. Specifically, each bank fires every 180 degrees. So you get one bank, 180 degrees of crankshaft rotation later, the next bank. You come up on another 180 degrees, the first one fires, then the second one. So it goes back and forth. So once again, the difference, sequential in firing order every 90 degrees. Batch fire, or what we're gonna do is bank to bank, is 1 bank every 180 degrees. Got it? Well, it really seems like there should be a difference. Batch fire seems super sloppy. Sequential seems super clean and sophisticated. We're gonna find out if it's true. And we're gonna do it on an LS engine, but the thing is, this is actually relevant for you if you've got an older muscle car engine and you wanna run EFI. All you need to do if you wanna do sequential injection on your muscle car engine, or on any engine really, is first of all, have a control box that can handle it. What we're running here is the Holley HP EFI box. It's a pretty basic box that can still handle sequential. Once you've got that, you also need to have a camshaft position sensor. On an LS engine or any modern engine, that's gonna be built in. You're already gonna have it. On an older muscle car engine, you can get a distributor, sometimes called a dual sync, that has a sensor built in. So that's how you would make this happen with like an older muscle car engine, or an older dyno operator like Steve Brule. See what I did there? I'm actually gonna ask the Steves about their sort of perception of sequential versus batch fire. But first, let's talk about the engine we're gonna do this with. We had to borrow this thing because we wanted big power from an LS7. Yeah, it's the General Motors LS7 architecture as built by American Heritage Performance. This thing is 442 cubic inches. Here's the basic rundown. It's a stock LS2 block, but it's got Darton sleeves for a big bore. That means 4.130 inches, 4 1/8 for the crank. It ends up to 442 cubic inches. It has 14-to-1 compression with a scat crank rods, Racetech pistons. It has a Comp Cams custom hydraulic roller camshaft. It's 245 duration on the intake, 266 on the exhaust, 660 lift, 115-degree lobe separation angle. The cylinder heads are a custom CNC ported unit called the Archangel from American Heritage Performance. And up top, we've got the Performance Design Carbon PTR intake manifold. This thing should make north of 700 horsepower. All right, now let me quiz the Steves and we'll get to making some noise. Before we even get going, I need to poll you guys. Dulcich.
I'm ready to go.
Yeah. What is your opinion sort of in the marketplace on the pros and cons or the differences, not technically, but philosophically, about batch versus sequential?
In the mind of Dulcich?
Yeah.
The sequential is more sophisticated and the batch is more primitive. So I've always kind of favored the capability of doing sequential. I don't know what the power advantage is, but I perceive that there would be.
Short version, batch is ham-fisted, sequential has the dosage precision. Now,
Yes.
I actually agree with you. That's sort of my perception too, but I don't think he thinks the same.
No.
I think you guys are crawling up the wrong tree.
Okay, why?
Well, because basically it comes down to time. I mean, you've got a valve that's open and closed. You've got an injector that fires. The injector could be firing at 80% duty cycle. The valve is open at 40% of the cycle. It's firing at the back of a closed valve, whether it's sequential
Or batch.
Or batch if it's at a lot of engine speed. I think a lot of the sequential stuff came from OEMs when they're looking for fuel economy and efficiency at cruise speeds. I think so much is going on so fast in race engine stuff or performance stuff, I don't think it matters. I think there's just a bunch of gas in there and it's all heading one direction.
You had an analogy for that once. What was it? When all the fuel is just sitting there on the table, waiting for a cylinder to gobble it up?
Right.
And you're saying it doesn't matter.
Well, I don't think it does. Not
In the performance world or in the whole world?
In the performance world, I don't think that sequential is nearly as critical as one might be for other reasons. Like I say, mileage, those sorts of things. I think batch works just fine for horsepower and wide open throttle.
Like low fuel demand situations, it has more time to follow the valve
More
action.
precision, as you
'Cause the
said.
duty
Yes,
cycles
it is a
can be
time
so
thing.
less.
Here's where I'm gonna have to just go ahead and disagree with you there. For a boosted application, guys absolutely are using sequential. But I think they're doing that because they see one plug that gets nipped and they put more fuel on that hole.
Of course. I mean, when you see an outlying cylinder that's 15 to 1, you'd like to fix it. We do the same thing with nitrous motors. That's no magic, no secret. We're not doing it necessarily for power. If you've got something that's way outlying and a cylinder that's bad, it needs to be fixed. But I think in multi-port fuel injection, you're not going to see tons of big outliers like we would in carbureted applications.
Especially on an application like this with a manifold that's pretty kind of okay. All right, so this is what we're here to actually sort out. We're gonna just look at bank-to-bank versus sequential. Our first run on this engine is going to be bank-to-bank.
Yay.
Yay, run it.
Baseline us.
Not that pretty of a curve, actually.
No, it's not. I mean, there's a couple things that are going on here. I mean, I think that particular intake manifold is kind of interesting in the fact that if you open the throttle body, there's about this much more runner hanging up into the plenum. So it's a much longer runner than we think.
Well, yeah, it looks like it's that long.
Yeah,
but
yeah,
it's that
kind
long.
of, exactly. And I think there's some resonance things going on there with potentially that runner hanging out into the plenum this far. It's hard to say, but we tried, and there is no tuning that bump out of it or dip.
When I say it's not pretty, it's like, we really like it when we fire something up and rip it and it's just got the perfect whoosh. And this one's sort of got some whoop-de-doos and bumps along the way. So it just means something's going on between the cam and the intake manifold and the resonance and stuff, and it's fine, right?
Well, I was just going to say, I mean, are those dips or are we just getting power bulges coming up here and there?
You're onto
There you
something.
go.
Some guys would look at this and love a double torque peak about 900 or 1,000 RPM apart.
So I'm going, this is bad, and you're going, this is good.
yeah.
That
Your cup
explains our
half empty or
personalities
half
right now.
full?
Perfect. Well, here's the half full that we're looking at. This thing made 617 pound-feet of torque at 5,300 RPM, and up at 7,100 RPM, we saw 717 horsepower. And that's really all there is until we start changing stuff up.
Go have more fun.
Next, just flip the switch, right? We're gonna go to sequential.
It's almost that simple in the Holley software.
Don't tune it up though. I want to see like the difference, just straight batch to batch versus sequential without changing the fuel table.
I think that's a good place to start.
Yeah, I just want to know what's different.
What it'll do,
It should be nothing, right?
right?
Yeah.
So Ishmael's gonna go ahead and do our initial switch over just from batch fire to sequential, and then we're gonna get even a little tougher and deeper into it after that.
So Brule and Ish have got it set now on sequential, but we've done no tuning. It's the same fuel map. We're gonna see what happens. that sequential, and it ended up being rich. We went in the room, messed with it a lot, tuned it up a lot, and here's the final answer. We made it through that nightmare, man. We put a lot of laps on this guy's engine. American Heritage Performance, thank you. Here are power numbers by the time we had tuned up the sequential fuel injection. We made 623 pound-feet of torque at 5,300 RPM, and this time it ran all the way up to 7,400 RPM, where it made 718.3 horsepower. So we did a lot of testing, figured out what was going on, and this curve here shows something that we don't normally show, which right here is how much fuel we are using in pounds per hour. This is literally a vein in our fuel hose that's telling how much fuel the engine is consuming. So it's not ratio, it's literal volume of fuel.
Yes, absolutely.
And you'll see when you add that to the graph, it sort of makes the dyno curve or the horsepower and torque curves look smoother as well, just because of the way it scales. Now I'm going to show you what happened when they flipped the switch and turned on the sequential fuel injection. Have you seen this yet?
No.
It's hideous.
Really?
Yeah. What went wrong here? Okay. This was completely unexpected. To be clear, the black lines here are when we had our bank-to-bank injection. The red lines are just turning on sequential without changing the fuel table. So why is it flowing so much more fuel and making so much less power?
I just like being right that batch fire works so well.
Well, I guess so. You were right about that. I'll wait till the end of the episode before I'm going to give you that one. But when we were eating lunch and I was telling Dulcich, man, I was doing the Dulcich, or the brulee head rub. I was like, I don't understand why we threw the switch and it's so much richer. And he just like comes right up with the answer.
You know, I really do have to give it to him because Steve, not being a guy who works with fuel injection every day,
Ever.
just kind of intuitively said, you know, some other things have to be going on. I think there's some time
Well,
factors
you would
that-
think it'd be exactly the same, but when you're firing it bank to bank as your strategy, each injector is firing twice as often as you are sequential. So that's open, close, and you have more dead time. So it's not going to flow as much fuel.
I know your logic flow went straight to like valve lift. It's actually area under the curve of fuel flow through the injector this time. What you're saying is that if it opens and closes and opens and closes, it's actually flowing less fuel than if you opened it once and closed it in the same time. In
The
same
duty cycle might be the same. And the other thing is, you know, when you close the door, that fuel stops and then has to accelerate again.
Right.
One more time.
So he was a genius for pulling that out.
I really have to give it to
was.
him. We're talking milliseconds, and it just turns into this whole thing. And I just, that was a really astute observation.
So to be clear on all of this conversation, the matter of fact is when you switch it from bank to bank to sequential, the sequential is going to get richer because it can flow more fuel because the injector is open longer because it just opens and closes once instead of opening and closing twice. Why would it open and close twice with the bank to bank? Well, because each bank fires twice per for 720 degrees of rotation.
Which is a cycle.
Which is a cycle, and so it flows half as much fuel, but does it twice. Bottom line is that it does make it way richer. And so after a lot of head rubbing, we went in there and figured it out and tuned it to death with Ish's help, and here's what we got. Boom. Now, the blue line here is our trouble one that was super rich and it was a disaster. And you can barely see the difference between the red line and the black line. One of them is bank to bank and one of them is sequential. And as you can see, it's the same thing. The bottom line is firing at sequential
More precisely.
more precisely as we thought doesn't necessarily add up to more performance. However, there's other things you can do as far as individual cylinder tuning. But let's have a look at our air-fuel ratio chart here. These are like the most confusing thing we ever show you on Engine Masters, except for sometimes when I get tongue-tied. This is going to be a graph of air-fuel ratio over RPM. Down here is RPM. Over here is 12 to 1, which is really rich. Up here is 14.5 to 1, which is really lean. Each of these segments represents 8 cylinders of the engine. For example, the black lines here are the bank-to-bank. Red lines are sequential. And there's so many black lines and so many red lines because it's all 8 cylinders. And what it allows us to do is, at a glance, kind of see which is packed more tightly and therefore having a smoother air-fuel ratio curve over RPM. And they're both tighter than what we typically see.
Certainly tighter than what we see with carburetors on top, but I got to give it to the sequential. It actually is a little bit tighter grouping.
And that tells us the distribution's better.
Sure.
Yeah.
Right. We've got a couple big outliers here. And with batch, or bank-to-bank, there's nothing we can do about that.
No, nothing.
But with sequential, we can. See, I wanted to do individual cylinder tuning in this entire episode, but the fact is this is all grouped so tightly. I mean, look at this. You're not going to improve that. Because to your point earlier, like, I was complaining about, let's just take this and group it more tightly. And you were like, at some point, it's still spraying gas at the back of the valve and the junk is splashing back.
Yeah.
And part of it is someone very wise once said, measurable but significant.
Right. Yeah, there's measurable and there's significant. It's not significant.
You know, and maybe we could measure an air-fuel difference by 2 or 3 tenths and we can go fix it, but did it do anything or change anything? Probably not.
Right. All right, so the next thing he's gonna do is go in there with Ish and just try and show you how they can tighten up the air-fuel ratio on those couple of cylinders that were real outliers.
Okay, one more try.
Yep.
Well, as you guys can see, we've got a couple of cylinders here, one being lean, one being rich. So Ish is actually gonna go in and he's gonna richen up number 6 cylinder right in this area, and he's gonna lean up number 2 cylinder right in this area, and try and flatten those out. Probably not gonna make any difference in power, but if you were a forced induction guy, it might help if you had a lean cylinder that you could pick away at, just to make sure you didn't damage anything.
Well, it took those guys just a few whacks at it, but you can see the results here. When we started with these black lines, these 2 cylinders were way up at 14.25 to 1 and 12 to 1. So way lean, way rich. They tightened it up right there. The result in power? 0. Yeah, absolutely nothing, and that's what we've seen before, which is why we haven't really gone through and tightened up every single cylinder. As much as I wanted to do individual cylinder tuning, you convinced me that in this application, it's just not worth it.
You know, sometimes you got to have something really bad to make it really good. And this was already pretty darn good. So there wasn't a lot of area to move to, but I think it was a great demonstration on what can be done.
Yeah.
And to your point, a blower guy with that 14.25 with 18 pounds of boost, he needs to be able to richen up that cylinder.
Or 35 pounds of boost. I mean, come on.
He doesn't want to richen every cylinder because then the power starts to go away.
Yep.
So it's very specific, and the sequential, I've got to hand it to it, is just more tunable.
So I think final conclusion, first of all, you were vindicated. Batch is good enough for an application like this. And you know what, 700 horsepower sort of, 442-inch motor is not a pooch. It's not super high-end race, but it's certainly, better than a typical cruiser.
How many guys have a 700 horsepower motor?
Not that many NA guys are cruising around with that.
Everybody I meet says they have a 700 horsepower motor.
Yeah,
What are you
that's
talking
true.
about?
But yeah, batch fire ends up just working fine for that. Sequential, I'm gonna still argue, is more precision and absolutely necessary for the higher the boost you go, the more nitrous you get, the more important that's gonna become just to save the engine.
I learned a lot today.
The big thing I learned, actually, was that bank-to-bank injection fires 1 bank every 180 degrees. And when it adds all up, it's the same amount of fuel flow technically as if you fire each individual cylinder in the firing order, except for the difference in the dead time in the injector. That, for me, is like the biggest walk away from this.
It's just informative. And, guys who do fuel injection every day, all day long, that's like, well, what? You didn't know that?
That's duh.
But, I mean, this was good stuff for me.
But take that back. We called some of these experts, and what did they say? The only thing I know is, no, what was the quote?
The only thing that's always the same is nothing.
Right,
Yeah.
that's it. We were trying to get definitions. What does batch fire mean? What does bank-to-bank
Well, it
mean?
depends on whether you're talking throttle bodies originally, or
Right.
you're talking semi-sequential or semi-batch fire, or if you're talking, 2 cylinders every 180 or 4 cylinders every 360. I mean,
Yep.
it got and everybody had a different opinion of what was correct.
And if you think about it, gathering all of those opinions and narrowing it down to something digestible and factual is what we attempt to do every single time on Engine Masters. I guess our first step is going to be a baseline with batch fire injection, which is kind of how we always do it. Go.
Do it. Go.
Leave. You know the fuel injector on the back of the valve? It's like when you're at the urinal and you're not peeing on the B, and all of a sudden you're wearing sandals and your feet are getting wet, and you're like, no, I gotta aim differently. That's what the injector's doing at the back of the valve. I'm gonna test 3 identical camshafts, at least as far as you know. I'm gonna explain the latest camshaft technology for valve train reliability, plus you're gonna see our 800 horsepower, 7,500 RPM big block. Look at this, I've got the whiteboard and everything. That's because this is going to get more technical than probably anything that you've seen on Engine Masters, but it's super cool and you're gonna understand more about camshafts than you did before. Here's our plan. We're gonna test 3 different cams that will appear to you to be identical if you're looking at your cam card or even the catalog. Here's the specs of all 3 cams that we're gonna test, and then I'll show you what's different about them. The duration at 50 thousandths tap at lift, which is something you'll learn more about in this episode, is 284 degrees on the intake and 292 on the exhaust. The lobe separation angle that we're not really gonna address is all the same, 112 degrees. The lift, also identical, 0.775 inches on the intake and 0.748 on the exhaust. So what can be different about these camshafts when the specs that I always give you on the show are the same? Well, it all has to do with what's called camshaft intensity, which has to do with the rate of lift per degree of crankshaft rotation. So let me show you the 3 cams that we're going to be running. First of all, we've got the baseline, which is a 90s style design, a fairly slow rate on that thing. High intensity, mid 2000s. That one has got a much steeper ramp. Then we've got the low shock, which is similar to the high intensity except for how the valve opens and closes, which is designed almost purely for longevity. There's one more thing that is different about these camshafts. The baseline has a lash setting of 26 thousandths and 28 thousandths. The high intensity and low shock has a tighter lash. It's 16 thousandths and 20 thousandths. As we get into the rest of this, I'll explain how that's going to affect our test and how all of this works. You can see that as the lobe rotates, it's got to have a ramp in it that moves this lifter upwards. The whole episode is going to be about how that ramp affects what happens at the valve. Let's look at the baseline rate of lift, and I'm going to express all of this in terms of a bicycle going across a ramp to a jump. This is just a wheel on that lifter, just like the front wheel of your bicycle. So let's say that you're riding along right here. You're Mr. Stick Figure, and you're riding your bike. If you're on a ramp on the baseline cam, you've got the ramp going roughly like this. But you've got that big 26 to 28 thousandths lash. So now imagine that the front of the ramp is cut off. So as the bicycle wheel is rolling over that ramp, first of all, it's got to hammer that little curb before it starts rising. And you can see how doing that would beat up parts in the valve train. Now the high intensity, this has a greater rate of lift. So your ramp is gonna end up at a steeper angle than it is on the baseline, and because it has less lash, it's gonna have a much smaller little curb right there. And then when we go to the low shock, and this is the real interesting part about reliability in the episode, your ramp is gonna have a little curve in it before it starts to climb. This part of the ramp is going to be essentially the same on the high intensity and the low shock, but it's that little curve right there that is gonna help this wheel maintain some longevity in addition to all the other valve train parts and especially the valve spring. Now let's look at a more technical view about how that is happening on the camshaft. I'm gonna take this graph right here and draw the trace of the lifter following the lobe. I'm gonna radically exaggerate everything so that you can sort of get the picture. On this graph right here, I've got lift in inches over here, and at the bottom, I've got crankshaft angle. So we're gonna be looking at rate of lift versus where the crankshaft is turned inside the engine, meaning where the piston position is. Now, remember that I told you that the duration at 50 thousandths tappet lift is the same on all of these. So let's just call this that point at 50 thousandths tappet lift. Remember, this right here is rise of the tappet. Now, we're also going to achieve the same total lift because every cam has the same lift. Now I'm going to go draw the baseline cam in green. Now I've got my high artwork here on the baseline cam. Let's look at the high intensity, which is going to have more lift per degree of crankshaft rotation. So it's going to start at about the same place. It's going to go through 50 thousandths tappet lift at the same place, but then it's gonna have way more meat on these two other sides, like so. Now, once again, I'm radically over-exaggerating this, but you can see that the 50 thousandths number is identical, but over here it's gonna get fatter. But now let's look at the low shock unit. I'm gonna do that in blue. Now, really the difference between the low shock is reliability. And so what it's gonna have is it's gonna open a little bit earlier, but it's gonna move really slowly, like so, up to that 50 thousandths number. After that, it is following the high intensity lobe. Ignore my art there. So the blue is actually going to be identical to the black. All we're seeing is that there's a much smoother ramp right there. And you can see that on my drawing of the bicycle. And that is the key to the episode here. Two things. There is the potential for more horsepower in many applications if you can open that valve faster. The reason is you can see that you've got the valve at a greater lift for longer. So there's a potential for more airflow. The other thing on the low shock is that that curve right there has proven itself to have greater reliability on the valve train. We, on Engine Masters, often judge camshafts not only based on this number right here, which is going to be at 50 thousandths tappet lift on both ends, but we also judge it at other points. We often look at what we call a 200 number, which would be 200 thousandths tappet lift. And remember, my scale might not be right here, but you get the idea. So the thing about checking the duration at 200 is look at this. This camshaft is over here at 200, whereas the old school 90s camshaft is right there at 200 thousandths lift. But let's draw a line straight down here to our crank angle number. And remember, this is these valves being open. And so therefore, the duration of this camshaft right here at 200 thousandths lift is way smaller than this camshaft, the high intensity is, at the same tappet lift. So the duration changes, and we know that duration can affect airflow into an engine, and in some cases it can affect the RPM range of the engine, or the RPM at which it makes peak power. One way or another, this often makes a difference. So that's how the different rate of lift can affect duration at different points on the camshaft. And honestly, you can check your duration at any point you want. 400 is a common one, but pick your point and you can actually get there. The thing is, it's not just the duration that changes. If you look at crankshaft angle or where the piston is, the lift changes between the baseline and the higher intensity camshaft, in this case, the low shock. Look at this. When the piston is at top dead center, the baseline cam has a lift of 223 thousandths, but the low shock is 264, a bigger number. 14 degrees after top dead center, it's 323 versus 369. 70 degrees after top dead center, big change, 666 versus 684. So you can see that the more modern camshafts have more lift at different points in the cycle, and what that means is it's also a greater rate of lift per degree of crankshaft rotation, which is kind of the point of this whole thing, with the exception of the huge deal in modern times. The cam that was developed like between 2018 and 2022 is the low shock, and it's all about reliability on the whole valve train. Comp Cams has tested this in Top Fuel and Pro Stock and Super Stock and mud boggers and tractor pullers and even on NASCAR stuff, and we know that the low shock with that ramp, like the bicycle jump, is gonna be easier on valve train parts, and that means replacing less stuff. This right here is the key to the reliability. It's gonna have that ramp instead of the curb. All right, now we're gonna roll into the dyno cell, and I'm gonna tell you all about the engine that we're gonna be running. I've given you all of the rocket science about the 3 camshafts that we're going to test here. The question is, will they make a difference on this combination? Here's what it is. It's a big block Chevrolet at 478 cubic inches. That's sort of an unusual displacement. Here's how I got there. We used a Dart Big M aftermarket block, so it has a bore of 4.5 inches. That's bigger than anything you could get in a production big block Chevy. The crankshaft, however, is short. It's 3.76 inches, which is like a factory 396 or 427. So it's only 478 cubic inches, which means I had to get some custom pistons made by JE Pistons to get the compression I wanted, which is 12.25 to 1. Kind of high. The cylinder heads that we're using are from Dart Machinery, and they are CNC ported. They have an inlet runner of 365 cc's. It's from their Pro 1 line. These things are stout. We've run them before, and we really like them. The intake manifold's an Edelbrock Super Victor, which is a big single plane for big power, and it's been ported by Wilson Manifolds. You can see that Wilson also put fuel rails and some fuel injectors in this thing for EFI, but we're not running that right now. Instead, it's gonna be all carburetor, and that carburetor is a Holley XP Dominator at 1150 CFM. So, is this gonna give us the results we want? Well, you don't know until you fire it up in the polygraph room and run it on the dyno. All right, guys, we have a lot to do. I say shut up and go fire it up, because this is gonna be a long day with 2 camshaft changes.
This is one of those episodes I hate and love all at the same time.
It's gonna be good info.
Good info and a lot of work. That's the downside. So
Yeah.
I guess there's just one place to go.
Yep, show them the
Get started.
baseline, yeah. Okay. Pretty good. 815.8 horsepower at 7,300 RPM. And the torque at 6,400 RPM is 608.7. I did some maths. Horsepower-wise, 1.7 horsepower per cubic inch.
That's good.
That's really decent. I mean, there has been a couple times when we've made a little more power.
Yeah.
But that was with a vacuum pump, with a little bigger cam. It had some other advantages that this doesn't have. I'm very pleased with where this is at.
Yeah, me too. I'm gonna do torque. 1.27 torque per cubic inch.
That's very good for a 112 LSA cam.
Yeah, that's the thing, is it's giving some up. And for the displacement, it's a huge head and a huge intake manifold. Well, we're about to put in, technically, more camshaft with the same duration at 50. You ready for a big time consuming, burning hot oil changeover?
Yes.
No, but we'll do it anyway.
Okay, let's go. Second camshaft coming in. With the high-intensity camshaft, we saw 808 horsepower and 608 pound-feet of torque, which doesn't mean much until we overlay it, but it looks like the numbers are down a little.
Let's take a look.
Not a big difference up here. I mean, 815 to 808 sounds like something, but that's just a little something going on up there at 7,400 RPM.
Yeah, we're talking, you know, 6 or 7 horsepower as far as a total difference.
What this is red cam is the baseline and the black line is the high intensity cam. Obviously, our cylinder head is not having any restriction that's causing it to just jump up 15 horsepower with the high intensity, clearly. And I think the little bump up at the top is who knows what. Down here, the increase in torque with the baseline cam, probably because the bigger lash makes it seem smaller.
That's certainly possible. This camshaft, the high intensity were never designed for down there.
No.
They were designed as drag race cams up in here. So
Yeah.
not a surprise.
I'm bummed. I mean, I thought it was going to make more horsepower, but
So did I, until you really dig into the combination and realize it probably wasn't starving for camshaft to begin with.
yeah,
Or area under the curve.
probably it would make more power if we had an inlet restriction like a bad manifold or a restrictor plate or a bad cylinder head.
We have
'Cause
enough of all of those.
We do.
Yeah.
But isn't it true that if you're running like a stock eliminator with a stock cylinder head, you add duration so
Yeah.
that the bad flow has longer to get air in there?
Yeah, and it doesn't necessarily make a higher peak number per se, but what it does is it'll drag it out further.
Yeah.
You know, it's just combinations are combinations. They're all very interesting, and that's why you develop things. You work on the same combination over and over. I mean, I've had 500-inch stuff where we ran a half a dozen camshafts looking for 10 horsepower. So,
Yep. But our conclusion on this is the reason that we're not seeing more horsepower is it's a lot of cylinder head, 365 cc head on a 478 cubic inch engine. Actually, now that we mention it, it's probably why the torque's a little bit soft too.
I think so. Yeah, that's certainly a possibility. I mean, up in that range, you know, part of it is these smaller motors, it's hard to get compression. And that's where a whole bunch of the torque comes from. So you put a big old camshaft with not a lot of compression, it's not going to be a big torque monster, but it'll still make good power.
Yeah. Ready to go with low shock? It only took us 2 hours to change the first cam. We're practiced now.
Yeah, we're warmed up.
Next cam swap incoming. Our low shock camshaft, just a speck down on horsepower up top versus the high intensity, 806.2, and the torque up a speck at 610.2. I'm calling that a wash.
Yeah, absolutely.
Yeah.
I mean, when you're looking at 2 horsepower, repeatability, change of weather throughout the day, we can tune for days and
I'm hoping that we just see an overlay. Can we pull up the high intensity versus this? It's got the same lobe above the lash ramp.
Right.
By the way, lash ramp is the point on the camshaft lobe that transitions from the base circle into the ramp that lifts up. And yes, I expected to see the exact same curve, and it is in here, but down here it's not. The red lines are the high intensity, and the black lines are the low shock. And it's interesting, the low shock is a little speck worse up to 5,200 RPM, and then it's better for a bump. Actually, it's better all the way up into here.
Yeah.
Then it's the same, and then it's just a speck worse up top, which is kind of unusual. Let's start with the low end. How come it did this? We know that the low shock opens a little earlier to start that smooth ramp before it starts to ramp in. Looking at the data, I saw that by the time we were at 6 thousandths valve lift, it was actually a speck bigger camshaft than the high intensity, but you know, just by half a degree or something.
Honestly, it's really, really close, but with the high intensity, you're snapping the valve open just a little harder, and that would give you a little bit of
it
an
may make
airflow
the
advantage
intake
right
port
there.
just a little more active initially.
Yeah.
Once again, this engine probably has low intake airspeed through the ports. How would that affect this? Maybe the snap helps it a little bit more. Maybe the low lift flow coming in earlier helps the exhaust get the intake running.
Well, generally, if you
These
snap...
are wild guesses, by the way.
Snapping it open is kind of an advantage as far as airflow and power, but realistically, the low shock cam is really not designed to operate or make power in that RPM range. It's
Not
a
at
drag
this
racing
size.
style cam or
Right.
a professional racing level cam.
My opinion is we're swapping twosies, threesies, you know, a little here, a little there. It's two different at the top. I mean, I'm going to call that basically the same. What I see in the advantage of the low shock is durability and longevity.
Oh, yeah, for sure.
And potential for parts to last, valve spring life, and potential engine speed, honestly.
I would pick reliability over this and that.
Any day.
100%.
Yes, any day.
I think that's the main thing. Overall in the episode, I'm honestly bummed that we didn't see a power gain with the high intensity. I know you expected that too. I think we've explained that based on the fact that the cylinder head is really big for the application, so there's not a restriction that demands more airflow.
And again, back to that development thing, I hate to keep kind of beating on that, but the bottom line is there's no one camshaft fix for everything in every combination, no one cylinder head that makes everything better, no one intake. I mean, it's a combination. That's why we work on this stuff and try to make it better.
You know, sometimes we sit here and we go, sometimes you win, sometimes you lose. In this case, I don't think we really did either one. We just found out that sometimes minute changes to a camshaft make minute changes in the power.
Right.
And that's it. But you know what? You gotta try it to find out. And that's what we do every single time on Engine Masters. Let's start with the low end. How come it did this? Steve?
I don't know.
That's why I didn't answer first. I was hoping it would be passed to someone else because I don't know.
Wow. It's also like, you know, a torture puzzle. It's like going into an escape room of Valve Train.
Well,
You gotta figure out the secret handshake.
Hello, xin chào các bạn nha, lại là mình đây. Hãy sang video hay cho các bạn xem. Các bạn ơi, các bạn thấy hay, hãy like và comment cho kênh của mình thật hay. Cảm ơn các bạn đã theo dõi kênh của mình. Thank you các bạn rất nhiều nhé. Gọi là quá nhiều kênh. Này lúc nãy sao tự dưng lại mở ra là cái tab này. Điện thoại. Đây là một đống sâu rồi. Đống sâu rồi, sâu ở trước. Bỏ ra view. Sâu nguồn trước 5 lít đây. Nguồn đợt trước 5 lít là giờ quay các thứ. Hắn còn mật khẩu ấy, tiêm. Hả? Lúc Git đói lắm rồi.
Đừng biết gọi vì tôi không có việc cả.
Đây nè, hắn còn cái mật khẩu thằng Văn Hùng 01 đây này. Hôm nay tự dưng lại lục ra được, tìm ra. Dạ, chốc tối cúp cả má này lên. Toàn sâu ngoan. Bây giờ rồi bát trước là làm view vãi đáy. Telefit chứ. Lên đi ra không lên. Con nó ra ngon. Mở là view. Ra xong. Những cái đấy thì đấy, như cái đấy ổng nhường cho anh, nhưng mà đẩy cái hôm bảo anh nhường cho anh, thôi để anh làm, thôi nhường cho anh, đã có sâu gì đâu. Mốc giờ quen, cái cóp đây này. Hả? Cóp trước làm, anh trước em làm đầy số ngon. Hả? Xe máy pha mà. Giống chịu chị. Đúng rồi, còn giống cả Linh này, Linh nguồn này. Ý. Nguồn đài. Ngon. Đấy. Đẳng cấp của
Đến giờ luôn.
hả? Đến giờ gì? Không, bảo anh mới là đẳng cấp thôi. Em bảo gì em đâu. Em bảo anh mới là đẳng cấp thôi. Em bảo đến giờ múc đâu. Qua có cái nguồn ấy ở ngoài. Giống gì? Chết mẹ.
Thức đêm test giờ có kết quả thế thì bọn chó nó sơi hết rồi.
Thôi bọn chó nhưng mà nó đổi lại cái bọn chó đổi lại được cái trong sạch người là may thì còn gì nữa.
Sạch cái cuối đời từ đây cũng gì. Anh đợi đấy.
Chả đi anh
đợi đấy, anh sẽ làm.
Dạ vậy.
Không đấy bán đất cạnh ở
Ở đây
đang bán cạnh ở
suất bao nhiêu?
cứ hỏi mất bố ai
Con đấy không phải tao hỏi nó chỉ suất đấy. Chỗ chợ hỏi em tâm linh sợ ma thì không bảo bây giờ cái đấy thôi em chịu.
về chính phủ đã làm cái bệnh không chủ án
Bố bài này cũng được tí.
ăn sa chim tu ấy.
đây
Về ăn C5 vậy là u sơ.
Đấy
À 24/7 đây rồi. Ui, còn phải đủ má. Cuối cùng tìm được.
công nhân
nhìn chay của quân. Chồng là bác mua mang về mới đi xong các giờ đang ăn đấy.
Sao nhỉ? Không cho vào. Dạ, có nguồn quay 24/7 247 một cái một kênh à? Nó bỏ vi phạm. Không bỏ vi phạm. Lâu đời lắm mà. Năm 2021 rồi. 2020, 2021, 2021 đúng không? Muốn nhớ gì nhỉ?
Bữa ăn TV show thì treo.
Hình như nguồn quay sao? Bóp nó sang đây. Thì như thế thật. Lâu rồi em không, nay em tìm thấy ngồi tự dưng lục ra đã nhiều cái kéo biết mình cất ở đâu. Trước ngồi test cả năm, test em anh luôn, test ngồi test kinh khủng. Cả như thế xem nó kiểu gì nhỉ? Có kiểu gì đấy nhỉ? Lạ nhỉ? Nét vuông rồi. Vuông qua mùa. Này thấy không?
We all have our interests and often spend quite some time. Won't that be great?
À. Cái gì ảo nhỉ? Khô. Chịu chết. Ảo nhỉ? bắt buộc cho vip về. Về phố thằng Tâm đấy á. Về phố. Thì ngó như tí. Dạ. 10 phút này cũng ăn luôn. Sáng đâu qua mua 8 phút đã 100 dạ dày rồi. Ăn no quá rồi đói quá thì đau. Có ở chua không? Ở chua. Chưa ở chua này không bị gọi là chữa được. Chưa ở nhà được. Trước em bị ở nước Vàng Khe. 4 sáng này uống cái rửa luôn.
Chia lại. Không biết đâu.
Cái đi xe máy gì? Đi cầm tiền trong cốp xe và tôi yên tâm. Để đây quyết nó lại đi gửi ngân hàng. Chịu chết. Anh mình nói mang tiếng. Có đi mượn. Vợ em kể hết rồi. Vợ em kể là chuẩn đấy. Riêng vợ em mà đã kể chỉ có chuẩn. Gửi độ đôi tỷ ngân hàng. Có phần, có trà để em theo cuộc sống. Vợ em kể hết rồi. Sao tao biết được? Anh cơ sở bên nhà ông Đô. Chịu anh. Giờ cơ sở ông Đô nữa điêu lắm. Lấy đâu ra. Em mà có tiền gửi ngân hàng cuộc sống mình đã sướng lắm rồi. Chả thế trả nợ đi chứ để làm cái gì. Nợ mang tiếng. Xin chào và hẹn gặp lại các bạn. Mình xin kết thúc video tại đây.